fourth lecture today. Is it on physical characterization of solid state organic semiconductor. Hope you remember what we have seen yesterday class. I just two slides to recap what we have done yesterday. Today the lecture is the third one, the physical characterization. Okay, in the first lecture we have seen that just introduction part, what is the necessity of this importance of organic electronics, how it will help to in future to complement it to the current existing electronics research field. Basically you have to understand that this is the material is very lightweight and we can able to go for large area printing. That is one of the biggest advantage of this organic electronics. And I talk about the importance of this field and everything we gone through that. The first lecture. The second lecture I have seen that how we can design the organic semiconductor. We have seen some of the design concept. So for each one of the things I go with the example, the conjugation length and the resonant energy and the substituents group and the interchain effect. All those things we have seen that how it will have a profound effect on changing the energy level of the organic semiconductor. Eventually the energy level is important to tune the property what we want according to the application, whether organic photovoltaic, transistor or light emitting device. Okay. And also I have seen that the another concept is donor acceptor concept. Based on this donor acceptor concept, how we can tune the band gap of things. That's push-pull effect. That is donor rich material will give the more electron push and electron deficient group will accept electron. So that push-pull effect will create a changing the band gap of the material. Okay, all those things we have seen. Now, okay, with this designing, by applying all these design criteria, we got a material. How we can characterize the material, whether we got material according to what we expected. So those characterization we saw. We have done some of the tutorial yesterday by using this one, basically how to define the band gap and see the energy levels. We have in this lecture we are going to see in this parameter, because this is 1 hour lecture. There are many characterizations available in addition to this one. I am only giving the characterization technique which is essential and which is important. So due to time limit we can't go through all the things. I am giving you only the important things one. Okay. Not limited to only these things available. There is a lot of things available. Even if you see that ultraviolet photoelectron spectroscopy, there is lot of options like photoelectron spectroscopy in air, that's called PISA, and other techniques. If you want structural, basically the structural techniques we have X-ray and all. Now I am going to say GVAX, because these devices particularly working on very thin layer. Okay. If you see, many of you know that how to take XRD spectrum. In the XRD spectrum, we use a powder sample and we fill it up with at least a few thick, and we do that. But in our case, we are not using the thick layer. It's very thin layer fill. Within the nanometer thickness, how the structural arrangement is there. Those studies we need to have intents like grazing incident, wide angle X-ray and the small angle X-ray, and also AFM and KPFM and TM. You may heard about all this technique, but just I want to know how this technique will useful in our field to characterize this material. Those concept I am going to talk in this class. Okay, I think I will finish it in 1 hour. Okay, so coming back to the overall criteria, I will give the photophysical characterization this one and the structural characterization. So if you see this one. So this absorption spectroscopy is, we have seen something yesterday, I will just go elaborate, and only cyclic, and the UPS spectroscopy, this for solid state spectroscopy that will decide what is your Fermi level and what is your HOMO level, HOMO-LUMO. And cyclic photometry technique is a liquid interface techniques that also will give information about your energy levels. If you see this, how to determine energy level, this is a completely, now you have to understand one thing. Yesterday many of you have some problem where the LUMO level come or where the HOMO level come. So I said this is a vacuum level. Vacuum level, again I am telling that, understand that Vacuum level is the level where the electron is set to free. Set to free, the electron is not on the surface, very close to the surface, slightly above the surface. That is only few nanometers just above the surface, but still on the surface only few nanometers, because it will give under the influence of some force is there, but slightly come out of the surface. That's called your vacuum level. Vacuum level means the level which is at high vacuum level, even though any surface near to the surface with a few nanometers, that's called vacuum level. Okay, that means the electron is already free. That's why it's called the energy level. The Fermi level it's called. I think in the middle there is one Fermi level is there. Fermi level only for metal, atom, everything else. The electron, the Fermi level, how much energy necessary to lift the electron from the Fermi level to vacuum level. That's called Fermi level. Okay. So in this case, your HOMO level is completely filled band, and LUMO level is unoccupied molecular orbital. It's not unfilled band. So this is, when you compare to the vacuum level, this is your LUMO, the top portion is LUMO. The still below is a HOMO. You got to understand this one, don't get it. So, okay. So in that case, if given the LUMO level, if you want to add, then we got to add up the band gap. In between this is a band gap. So if I ask about, if you know the HOMO, if you want to find out the LUMO, just from the HOMO you subtract the band gap, you will get LUMO. Okay. Don't blindly take, subtract or add anything else. Understand this concept, because the y-axis is here is all are negative, because everything is in there, because these are all dealing with your electron energy levels. Electron charge is always minus. That's why we keep everything in minus. You got it? Because everything is here, you got to understand everything play around with the electron, because plus means is absence of electron is plus. You got to understand. If there is an atom is neutral, when light hit on the atom, then electron will go out. When the electron is separated, the electron is negative charge. The absence of electron is called hole, that is plus charge. You got it? So that's a chance. There is no, we can't, by nature we can't, there is no holes. There is absence of electron is called holes. Okay, that called plus positive charge here. That is in inorganic semiconductor. In essence, when you talk about in our organic semiconductor, because as I said, organic semiconductor, all these charge carrier moves under the influence of your the atomic vibration. That's called photon. So the electron photon interaction is a quasi particle give. That's called is a that's called is a polaron. So we call it as a polaron in case of organic semiconductor. Okay, but for simplicity, we'll consider is a holes and electron. Okay, okay, and this is an photophysical characterization. Photophysical means all these characterization involve light. Even though we time. Okay, we absorption spectroscopy also we input all the visible light, the range of 250 to 1100. We are going to see this demonstration this afternoon. We will having the hands-on experience. Which one? Yeah. This is a simple representation of atom. How is atom structure? We know that anything, if it is any semiconductor, there is the conductivity is a band conductivity. Band means it is conditions a valence band, conduction band. Okay, that's Fermi level. This atomic structure. How we probe this? There are two different ways. Probing is absorption spectroscopy and UPS spectroscopy. We probe to find out what is exact energy levels. Okay. Okay. These are all photophysical. This is enough. And the other thing is structural characterization. Structural characterization using this synthesis material, whether in the device case we always make a film, because everything is atomic. We can also make a solid state film, that is a DRS spectrum we can take. We make a film, and when in the film we need to find the how the structural arrangement is there. How is it? Because in crystal everything is a regular arrangement of atoms in crystal. If it is amorphous, if it is zigzag, if it is not regular arrangement, is called amorphous phase. Okay, that structural arrangement is dominantly affect your device property. If the structural arrangement are regular, then we can get a conductivity is improved. That's why all the crystals have high conductivity. You know that. So if you want to find out why the device is working, why device is not working, it's really necessary to understand how this structure is there. Then we can relate this called structure property relationship. So the structural arrangements we can decide first GVAX and GSAX. GVAX is grazing incident, wide angle X-ray, this is small angle X-ray. Okay, that will be all the structural. We can probe the whole depth of the structure because this is only the 100 nanometer. Okay, the second one is atomic force microscopy, and K is Kelvin probe microscopy. Atomic probe microscopy, I think most of you know that. Anyway, I'm going to explain. This is a technique we know how is the morphology of the surface, because basically it uses a small nano level probe on scanning on the surface of the any layers, any film, and find out how is the morphology is changing. Any nano level changes it can detect how much, because in our material all the domain size is in nano level. So I'm going to say some example how is it looks like and what is the required surface we need for the efficient performance, for the optimum performance of the device. Okay, so the structural, then tomography. So tomography is nothing but how the section wise it will give the analysis. That's thing. If you see the substrate, this is I'm saying that the molecular can again let's say stack like this things. Okay, stacking. This thing maybe is a Piper stacking. Sometimes it may do it may go for 90-degree tilt. That other stacking will be there. For example, for most of the cases, for example, if you know the silicon solar cell, we have the P junction, N junction, right? We have the heterojunction, because P and N. That concept we already seen that. We have at least two, P and N type. Then only we can make a diode. You understand that the OLED and OPV is basically is a diode. If you have a diode means we need to have a P and N type material. Okay. So most of the organic solar cell we have the P and N type material. We mix together. Then we introduce another concept called bulk heterojunction. Normally, you know, heterojunction we need to make. So in this heterojunction, we have two different phases. If you have this lengthier chain, this is normally is called P-type polymer. If you have the circle things, it's a small molecule. Small molecule is always small. This is a P-type and N-type. This P and N-type material like this is arranging like domain-like things. So how this, if you see this is the smaller domain will be regularly arranged, not in whole bulk, but at the domain level, at the nanoscale level, it can arrange like this. Yeah, some material will be like this, any current. How is it arranging? That we can probe by using GVAX. The other thing is, this is in 3D whole. This is on the layer type. At the bulk, how is it? This is, if you have this purple color, these are P-type donor phase, and if it is white, means this acceptor phase. Like this, donor and acceptors are distributed like this, okay? And really, so how this is donor acceptor distribution helping for device performance, we are going to see that, okay? So this is some of the figure. This is EFM figure. You can see that there are a white color short spot and them are dark one. So this is a phase difference of your donor and acceptor things, okay, I'm saying. So this is something looks like your GVAX data, GVAX, we can get the reflections, the atomic plane reflection here. Normally this 010 reflection will normally tell you that how the molecules are arranged in the stack. It's called as I said, the conjugated material always having the pi electron, okay. Pi electron have the attraction. When you have the backbone is always phenyl or thiophenol group, pi electron will be there. The another layer molecule will stack on this. So like this, if you go stack on, in between is the pi electron have the more interacting each other. It will stack together. Then it will have a regular arrangement of this pi electron. This pi stacking, that's called pi stacking, is preferable arrangements for charge transport. Okay. Suppose one layer is like this, other atom is coming like this vertical. This is unfavorable for charge transport. So pi electron only will conduct charges in this case. So those type of things we can. This is a TM picture. How the domains are arranged, we can see that. So how I will little bit go through that. How to take this characterization, and from this data, what we can infer from the data, and how we can correlate the data and actual structure is presented in the prepared film. Okay. Anyway, eventually after preparing film, we are going to make a whole device, and this is one of the aspects. Okay. So next slide, I am saying that this slide already go through that. No, you already well known. Basically, it's top energy of photon. This is I can see the example here. If you have the same material, how we work on in solution phase, in thin film phase, in crystal phase. So yesterday someone asking why this one. This is a properties of different state of matter, because any material it will behave differently in what phase is available, whether liquid, solid or gas. Okay. So now this is liquid state, the absorption is high wavelength, and this is called bathochromic shift. They call the absorption is going to red shift, because red shift means if anything, infrared is around beyond 8. If anything towards a longer wavelength, that's called red shift. If it is going to the shorter wavelength, it's called blue shift. I think you know that, I think. So this red shift, it's a representation of the arrangement of atomic structure or molecules are regular, becoming more regular and regular. That's what respecting red shift. That's why we get red shift in film is more, and crystal is even more. The crystal is more ordered structure. Okay, and this is both we are giving. This is absorption. This is PL. Normally, the atom emit at particular wavelength. After that, it will emit energy which is lesser than what it absorbs. So that's quite expectable. That's what this energy is less than what is absorbed. Okay, so that is a PL emission. Okay, so as I said, we can calculate from this absorption. We can calculate what is the band gap, the material. We can see that. As I said again, according to band gap, by adjusting the band gap only, then whatever the material we synthesize is going to absorb, harvesting what wavelength it is going to harvest, we can predict that. Okay. Okay, next is already so that cyclic ultrametry, and already you know very well about this formula to use calculate HOMO level and LUMO level. This is a simple CV spectrum for things. This is a molecular arrangement of in highest HOMO and LUMO level. This is some of the actual spectrum of your cyclic voltammetry. This is some of the molecule given SMX and Y. If you have the all is negative, it's called reduction peak. So how, as I said yesterday, the reduction peak is calculated by where is the onset is starting, this place. This is for this one, and in this case it's starting from here, and in this. So from this one it calculate. If for example, if you have this is around 0.9 around something, if it is from 4.8, if you subtract this amount, you will get 3.95. So that is your LUMO level. Similarly, the HOMO level onset also, you onset actually you can get the tangent here, and you need to another the baseline tangent here. Where is cutting, that's point we need to take it. The same thing you follow for absorption spectrum also. This is a correct way of getting what is the answer to calculate this HOMO level. I think now we understand, you can understand here, I draw the one line here. This is a baseline line here. For this one, this is a tangent for the where it's starting the oxidation. So this meeting point only you can consider taking the onset. I think, hope you know clear about this one. Okay, do that. So this is some of the example I am giving here also calculated. You always, any organic compound, there should be one oxidation potential, there should be one reduction. Okay, because we are designing the material like that, you should get. But some of these highly N-type material like PCBM and all, sometimes it's if you have multiple electron reduction, one or more than 1 or 2 electrons, you may not see that. In that case, you define this LUMO level first. By using the band gap, you can find out what is the HOMO level. Okay, that's fine. Okay, since you know, I will skip to the next one. So again, UPS also I little bit gone through yesterday. How is the UPS? UPS also same thing. You can find out what is the Fermi level. Fermi level is mostly we found it for metal atoms, mostly silver or anything. They don't have any HOMO level because HOMO LUMO level is merged together in metal, so that will give only Fermi level. Only the semiconductor we can get valence bond, conduction bond. In other words, it's a HOMO level, LUMO level. Okay, and here what the thing is, here this little bit difference from AUPS and XPS, both are used the same instrument. It's all ultra high vacuum. We put the sample in ultra high vacuum in vacuum chamber and vacuum it around 10 power minus 9 actually, minus 9. We need to have that much interaction. So when you probe this one, we use X-ray for XPS, and we use input light is a ultraviolet photon for UPS spectrum. That's the only difference. So when you do the X-ray, what is doing? The X-ray is a high energetic wave. It go and probe your K cell electron. You know what? In a little bit you understand your atomic structure. Around the nucleus, the first cell is called K cell. KL, Mn it will go, right? The KL is only you have 2 electrons, then remaining is called 210, like this it will go. So it will go to the very basic, very first electron it will touch, okay, XPS. So we can get all the information is one atom is, whether it is a small atom or a big atom, then we can find all the chemical information by doing XPS, okay. But in our purpose we are UPS, comparing to XPS, UPS is a low energy comparing to X-ray I am talking about. Then it cannot go up to that high energy, up to that close to the nucleus, but only come to the surface level. What is the valence band? Valence band is outermost electron, frontier orbitals, okay. In the frontier orbitals, this is a top electron, 2p electron. So those electron will be come out during when you do that low electron, because everything depends on what we are probing. If you suppose, sorry. Yeah, okay. Yeah. So this energy is enough to probe only the surface atom, the valence band electron, and also in top of the valence band, as I said here, in between, on top of this is a valence band, on top of here in between Fermi level. The Fermi level also you can probe actually, that's all, okay. The HOMO level is here, the Fermi level is somewhere here next time. So once you get Fermi level here, then after the Fermi level, another small energy level only we are trying to add up. Yesterday that's all saying that we want HOMO level, try the cutoff energy level, that's called Fermi, then add your HOMO, from the HOMO onset. I'm going. Yeah, here I'm saying, yeah, okay, here is, if you metal, this is Fermi level. This is in the semiconductor, you have a valence band and conduction band here. So when you skip the atom, so the electron will, this normally if you see the spectrum of this one, so there is a cutoff energy will come around from the Fermi level. So the simple spectrum is given here. When you have a UV light source, this is your binding energy, then it will hit your valence electron, this electron will come out. What we are measuring in the UPS spectrum is, we are measuring the kinetic energy of the ejected electron. So whatever the UV light input energy is given, this energy is used to liberate the electron from here. That's called, the energy should exceed the binding energy of some of the electrons have the binding energy to bind the atom. That binding energy plus which energy is coming out. So that is your equivalent to your input energy and the output energy. So as I said here, everything explained here, core electron is ejected here, and this is work function. So in this case, this in UPS spectra, this is energy in, energy out. The input energy is given kinetic energy plus binding energy. Then the x-axis we are giving is binding energy. So binding energy is nothing but the input energy minus kinetic energy. So if whatever electron is going in, if it come out, means there is no effect is going on, because the energy is highly bound. That's why we are getting here 0. When some of the things come out, first thing is your Fermi level electron is come out, means that's called your secondary level electron. So that's why this point is called a secondary electron cutoff. Secondary electron is cutoff, means the electron at Fermi level will come out first. That's called secondary electron cutoff. Okay, this is your secondary electron. After that, our energy, this minimum, we can have a small onset here. This is for metal. Metal, normally you don't see any HOMO level. That's why this level is around 0. But if you see any other metal oxide, this is not 0. There will be some onset will be here. You can compare these two spectrum. This is a UPS spectrum for metal. So metal, there is no HOMO level, but other things you can see the HOMO level of some 2.3. And this is your Fermi level, all the things. So catch new my cutoff, this is Fermi. Then in the additional case, we add this one. Actually, this one should be plus answer you will get. Totally, you will take a minus over here. Okay, this second electron. This is some of the things how to calculate. Normally in the higher level, this is called Fermi level. And at the lower energy side, we can see how to calculate the HOMO level I am given. So in addition to that, there is one more spectrum of IPS spectrum. IPS spectrum is nothing. This is UPS ultraviolet. This is the inverse photoelectron spectroscopy. What this inverse photoelectron spectroscopy gives means, this is give the LUMO level actually. Normally we don't do that. Now recently this one, what they can also do, because this spectrum is stop up to 0. This one is going beyond 0. How this is work is, here we use input UV electron and we input UV photon and electron is come out. In the inverse case, what they are doing, they put electron, they impinge the electron, then find out the UV photon out. Like this, they do the inverse effect and find out the LUMO level of this material. Okay. So next, this is some of the device data. We use this type of PFNBR is one of the electron transport layer with the mix with the melamine, and they did a device fabrication, and they just find out by using the UPS spectroscopy, they improve the electron, they tune the conductivity of this electron transport layer. This is electron transport layer. By mixing with this one, they studied how the energy levels are tuned. Here, if you see that there is a small difference in the cutoff energy level when you mix PFNBR with the methyl ammonium. There is a 0.03 difference is there. In the HOMO level also there is a shift in 2.07 to 2.16. That make a huge difference in device performance. It's going from 15.9 to 18.58%. This is one of the best sell in organic photovoltaic. By doing this type of energy level tuning, we can further improve the efficiency of device performance. How is things? So far we see that how to probe the energy levels of the material. Okay, so this is one of the things we can, by doping we can tune the energy level. One thing, that doping, how is it helpful in devices? This is one of the example, because they are doping the things with the 0.25 MA doping, because when you dope this one, the doping changing the energy level of this material. So once it's changing, always they see that when you do 15 to 16, and this example 18 to 18.5 told us, there is always, you can see the improvement in the device performance. Okay, this is the necessity of what we are doing. Okay, how this your energy level changes affect your device performance. There is some effect because we want to do something, studying, finally end up why it's necessary, because this is necessary. Ultimately, we want to have a very good performance and improved performance. It's helping for that one. That's why this is more important. Okay. So now I am giving, so now you can have one question. Okay, we are studying the energy levels in CV, cyclic voltammetry as well. We are studying the same energy level using UPS. Is one of the time consuming term, because in UPS if you work on, you go to wait for pump down vacuum, and we need a sophisticated energy instrumentation and everything else. But when you do to CV is very simple. We know that just to prepare a solution and put an electrode and we can easily find. This is easy, and this one, then how the data quality, how is it comparable? So that's why these things give, that's why this give the things. This is the hard surface will give UPS. The dotted line will give the energy levels from the CV. Okay, but almost the band gap looks like there is small ups and down is there. Both are not exactly same. I'm saying, I have to say that, because I say that for solid state wise UPS level, it's an exact one, I can say that. But so even we can't able to access all the time UPS, we can do cyclic, but it's not bad. We can also come, if you have a 2-3 synthesis, which material is level is comparing to one. Normally when you do this one, always we need to have the reference material. Like for example, for any material we have a very standard P3ST, we do that material. Comparing to that one, how is it varying? Okay, then we can find out how is the things. When you have a reference, with the reference one, we can find out what is new material is HOMO level, LUMO level changes. So for if the P3ST level, if it is changes is like this, for whatever the new material, so it should be shifting. When you do the things, compare, right? Then according to that, there will be a little bit different will be there from the CV, because always we can able to do only CV to find the energy levels. So for actual things in solid state, what it will be, we can also see that. Okay, so this but the variation is always linear. You can say this is oxidation potential ionization energy of this is for UPS, and this one, when they fit, it will linearly varying. It's not drastically varying, but there is a small difference in this one. Okay, so we have seen some example of from all this material and find out how these two techniques are varying in the measurements. So this will give some idea about this one. Okay. Okay, next thing is I am going to talk about the film characterization. Before doing how we are characterizing film, first I need to tell you how we make the film. Okay, in actually with respect to photovoltaic, organic photovoltaic. As I said, um, as I said, for any photovoltaic, we need to go P and N junction. Okay. In OPV device, what we are doing, we take this P-type material and N-type material, we dissolve in solution and mix together. We thoroughly mix it for more than 3 to 4 hours time. The very good blending. After blending, we use a spin coater and spin and make a film. You know, the spin coater is just to make this solution and putting it out of any substrate, because normally we coat it on like this on type of ITO substrate. Okay, ITO, then P dot is some of the whole transport layer, we put it. So this is your active layer. Okay, by mixing we coat it on the substrate. Then we do annealing, because after that, because we are coating from the liquid surface, after making the film, we just heat it for some time so that all the solvent will evaporate, then film will be formed. Then on making the film, on top we make the electron transport layer and the metal contact, so that we can charge, we can easily. This is actually simple device fabrication, how we make the organic photovoltaic. So this is your whole transport layer, the calcium is electron transport layer, and the aluminum is your metal contact to extract the electron. The ITO, the transparent conductor, that's extract your holes. Okay, this is simple structure. So now all the device performance going to majoritarily is going to affect by the structural composition of your active layer. So now we are going to probe what is structural configuration, because this is very, very small, very thin layer, and the domain size are in nanometer level. Because layer itself 100 to 150 nanometer thick. Okay, that's why it's challenging. We need to have a highly some sophisticated technique to characterize this one. Okay, so this is what we make a film. Okay. Okay, so now I am saying that what are the changes you can expect in the film? One is the phase separation. Second is a molecular packing and interfacial orientation. Interfacial orientation means both is a donor and acceptor is there. Both the interface, how is it orient, that also varying. You see, this may be the P type and you see N type. Sometimes it may be like this, it can have a P-pi stacking. Something one layer is horizontal, other layer is vertical, interface orientation. Something we can have the pi-pi stacking, and sometimes we have the vertical lamellar stacking like this. And in overall the three legs, this type of big domain of continuous network of is acceptor domain, this is donor domain. So we can have this type of different level of, so this will be in surface level, this will be bulk level, these two things. So this type of arrangement is called edge, they call. Suppose if the layer is complete like flat like this, it's called face on. The layer is, so the face, instead of molecule is standing like this, it's called edge on. Because if you consider the tri-fin ring, tri-fin is, if it is flat, then all the pi-pi interaction go. Instead of flat means is parallel to your substrate, it's called flat. Because your substrate, your I2 substrate like this, if the molecule is lying on like this, it's called face on. The face is down. If it is tilt like the 90 degree, then it's edge on. That's why. That's the meaning we call edge on and face on. Here I said the face on is direct transport to electrode, inefficient charge transport in edge on. Why I said inefficient charge transport is, normally if your surface is like this, if your pi electron is parallel to the surface, so it will easily transport to the surface the electron, because the pi electron is facilitated the charge transport. But instead of that, if it is arranged like this in vertical, where pi electron is here, the charge transfer may not be efficient. So that's why edge-on arrangement is inefficient for charge transport. That's why this type of information we can get it from GVAC studies. How is it? Okay. Other thing is nanoscale phase separated morphology. Nanoscale means in overall how the donor phase is, because we are mixing the two phases together, how the donor phase is there, how is accepted, where is these phases are located. Those also will change the device performance. Okay. So, okay, now this is simple about GVAC studies. Have structural knowledge. In the GVACs, what we are doing is, so this is your sample. Okay. In this sample, what we are doing is the X-ray, the dotted line, it shows the X-ray. The X-ray will incident on the very small angle. When we do very small angle, it will hit here and the reflected beam it go. When you have the detector, this is a detector which detects the X-ray. When the detector is very near to them, this is called grazing incident, wide angle X-ray. If the detector is somewhat away from the distance, it's called small angle. The same thing where we are detecting. When you have a when your detector is away from this one, even the surface level, very surface level things we can observe here, the surface morphology. When the detector is nearby, even little bit depth or information, because if we change the wide angle, if you make it wide and wide, then it will go into the depth, in deep of the surface. It will go little bit deeper to surface. Then we can do the bulk information of the layer, because if you see, you imagine that this layer is only we are having 100 nanometer. Okay, the X-ray, by changing this wide angle, and we can probe what is underneath of your surface level, because the 100 nanometer in the top layer. So what is there in below 5 nanometer, another below 5 nanometer, we need to say how is the arrangements. So those arrangements we can get it from this GVAX data. Okay, this will give out like this. This is the incident radiation. So then it will have this middle one is a direct beam. The scanning will be either in up, come, and also do the sidewise as well, these things. Okay, so all these three-dimensional variations we are plotting in a 2D. That's why the evolved sphere is coming. That's why if you have all the spectrum, the middle spot will be something block out. That's because the reflected beam start. We are having the we are having the plane detector, 2D plane detector, but the radius will be the distance, path distance traveled by the X-ray, the reflected beam is different, because this length is different from when the rays is different from. That's why this type of the block line is coming out to adjust that variations. The things are, that's a data plotting error. Okay, so in this GVAX studies, we can probe whether the molecules are arranging in face on or edge on, or how the domain size are arranging. And this one we can get it from TEM studies. TEM is another studies, because in the bulk, I think you heard about what is TEM. TEM is nothing but a transmission electron microscope. If you make a thin film, the ray will transmit, then you will tell how is that morphology and all. So TEM will say bulk, because in the whole bulk the electron ray will be transmitted and we will get the information. Okay. So from GVAX we can study how crystallinity, because how the things are very crystalline arrangement, crystallinity, and how is the crystalline orientation, whether it's oriented in tilted way like this, all this orientation we can find out, and also we can find what is the crystallite size. As I said, if you have this type of crystallite size, after it, the orientation is different. So what is this crystallite size? Those things also we can get it, and also interlayer spacing. What is the spacing between the layers? So those information we can get it from GVAX. Yes, sir. Very ultra thin layer. And TM is another thing still, but GSAX will give the domain size. This type of domain size we can get it. Okay. So this is some of the different possible arrangements and how the GVAX is used to probe this one. For example, this is just same as this one I'm giving more example. If your arrangements like this, how the reflection will come. Okay. So in this case, if your grazing incidence is going to hit like this, okay, then because of there is a structural gap is there, the electron reflections go up. So if you have suppose if you have this pi stack arrangements, you can expect a peak at 0, 1, 0 position. If the molecular arrangements are in pi stacking, you can always expect the peak at 0, 1, 0. Then we can find out, okay, you got a pi stacking. Okay. In contrast, if you have the arrangements is like this, the 0, 1, 0 arrangements will be coming like this, because when the arrangement is like this, the ray cannot deflect over there, because the reflection can come out only in this direction, the x direction only, the 0, 1, 0 peak will come. So this 0, 1, 0 peak exactly at, if you see the QXY direction, it's around 1.6, the 0. We need to find out where is 0, 1, 0. If 0, 1, 0 is coming, the plane is coming at in x-axis, this is called your end-on, so this is called edge-on orientation. If it is come at 0.10, it's called edge-on. At the same time, you can also get various peak, 100, 200 peak. That peak will tell you about how the interline spacing and arrangement is there. Okay, other peaks. So there are different arrangements, and I tell what is the name of these arrangements. I said you already well known what is this one. This is pi stacked one. There is a face on. Again, face on means this is if a substrate is like this, the the back pole of diaphragm is the p electron is just phase on to surface. That's called phase on. Okay. Edge on means if the phase on is 90 degree to phase on is this called edge on. Okay. Another thing is called end on. End on means instead of like this, if you have another section, if it like this, end point is like this, it's called end on. I think, hope you know the difference of this one, end on. So because the molecule is end to end, okay, face to face, that's called end on. So the molecule can arrange like this. One is face on, edge on, and end on. And sometimes one layer can be tilt like this, and one layer can be tilt this way, tilt angle and all. Sometimes it get disorder. Some case, if there is no interaction is there, one molecule like this, one molecule end on, something you can tilt on, anything, it can have the multiple orientations, okay, that also possible. So this type of possible arrangements is we can detect through GVACs, okay. So this will give some of the things. So by saying this one, just now I said, if it is any reflection, if you see 0, 1, 0 reflection here, 0, 1, 0, then we can see that is face on orientation. So okay, this is one example I am saying that if you see this is your 0, 1, 0 peak. So here, when you see this one, we don't have any 0, 1, 0 peak. So this is not a phase on. If it is phase on means the peak should be here like this. Now we have a broad peak here, around 1.5, this is called phase on. But instead of this one, you have peak at 1.6 in this one. If it is in this one, this is called edge on. The same thing, if your peak is around this x-axis, this is called end on. If this is this peak around, this is our phase on. So they say that's why it's called phase on, this is edge on. This isotropic. Isotropic means it will be in a regular arrangement. For example, if you have the film with PCBM, you know, this very spherical shape. So spherical shape arrangement is everywhere is the same structure. In the 3-dimensional level, everywhere is the same arrangement. If you do anything particularly in PCBM in the material, that will give this type of isotropic reflections in this one. Okay. So this type of things will give up, you have to remember what at least the 0, 1, 0 direction will give always a pipette stacking. Okay. Now I just giving little bit comparison about how these GVACs and structural things are there. Some of the molecule, this molecule is BDT, the FEH based molecule, and they say this is top is GVACs, and the bottom is atomic force microscope, and the bottom peak is a TEM of. So this we can say the nanoscale phase arrangement of this one. So this we can see that we can see the reflection at this one FF molecule. They're around pipette stacking, and this one also is improved one. So all the functional chlorinated molecule, it shows that it's all pipette stacked, whereas here is we can see very feeble one, less one. But all those AFM and TM structures, we can see that there is very nanoscale level domain size is forming. These are all. If you see that this scale is only 2 micron, so the small things around 100 micron. If you see again, everything the scale is same. So we can see the nanoscale arrangement is overall distributed in this plane. Okay. This one. So this is another example. We say how is a phase on edge on. As I said previously explained. If you any peak, if you get it around 1.6, then you can say phase on. So if it is no, the vertical line is there is no peak there, then it's predominantly it's a edge on. You can say that. At least if you don't understand the whole all arrangement, at least you can where you are expecting the reflection peak, if it is phase on, if it is edge on. Okay. I think now you got a point actually to what is phase on, actually edge on. Those things you should understand right now. Okay. So in this BTR based molecule, so in this BTR blend, so this is arrangement is exactly like phase on. That's why if it is phase on at vertical axis, we can get Z direction, we can get a peak around here. We can say the broad peak over here. So that's why we are getting this type of arrangement. Rather, if you have this molecule, the side chains are varying. The side chains are varying with the rhodamine, and this is silol group and this thioester group. So by substituting different side group in this molecule, we are getting the different structural arrangements. Okay. So here we are getting broader phase on, but when you have the tips substituents, what you are getting is we don't see the peak from in this direction. We only peak from 1.6. So this is predominantly in edge on position. So because of this edge on orientation, which is not favorable for charge transport, that's why we compare the performance of these devices. We are getting very low, 8.3, whereas this device is getting around 11.1. So that's why I'm saying that these structural arrangements reflect in what your device performance, which is due to your inefficient charge transport, that will affected by your the arrangements of molecule. How is it? So this way, if the device is not working, we can't blame that always. Oh, it's a material quality. No, how we are arranging this structural on the film, that will make. That's what device physicists, all the device engineers will say, how to make a film. We say that if we spin coat, we can make a film. Not. There are various methods, solvent or vapor annealing. Those methods I am going to discuss in Thursday. How to make a perfect film by doing different optimizations. Those things I am discussing in the device fabrications. But this one I am saying that if it is different orientation is forming, how to characterize and how is surveying. In that case, if you make a film, then if you yourself analyze the film and characterize and you yourself make the device out of it, then only from the device performance you can go back what is the structure and go back what is the device molecular structure. If all this linking, then only you come to the picture, okay, this because you are starting from everything is a molecular design. So this device is good or this device is bad. From getting all those information, then we can conclusion that okay, this molecule can work, other things cannot work. So by having one data, we can't say anything else just by giving data. So we need to. That's why I am going through that first design, then characterizations. Then I will come to that how to get a very controlled way of molecular film arrangements. Then we make how to make a very good devices. Okay. So from this information I'm going. So once you finish this course, you'll find out all those things. So now I am saying that only how to characterize. Okay. So this is another. This is the same molecule, GVAX. So this is giving the how the morphology. So that is the GVAX data. This is AFM data. Sorry, not G. I put GVAX, but this is AFM data morphology. Morphology means AFM. So this device BTR-Y6 is giving the regular. We can see the nanoscale morphology of these things. When you have the typhine one, we have some elongated type morphology. But when come to BTR tips, the morphology is so spread and the small size is very too small. Not if you say here is a bigger domain like 30 nanometer. If you see this small line, is more than very 10. Here the morphology is a smaller domain is it's always good, but too much small also not good. Very too much small also, because too much 10 nanometer device, no, then because you got to understand that in this domain the exciton is the light absorbing, after absorbing a light it will create a exciton. Exciton will travel to the anyway this concept I will go through in the I think next class, I think how the exciton is charge separations. There should be some 30 nanometer device is traveled through, okay, otherwise it will go to recombine everything else. So we need to have a little bit decent size. This is very small, that's why the performance is very poor in this case. Okay. So this also AFM picture and giving a very different morphology for different film, not the same thing. And so this was a little bit said how, I don't know how much you know how the AFM technology works, because AFM is a surface based technology. We use a small nano level probe to scan on the surface. So when the tip is scanned on the surface, on the back side of the tip we have the laser light. So when the tip is, so this is AFM arrangements. So this is a cantilever, there is a tip around it, the tip is like this, you can see the tip, imagine. This tip will go to the surface. Imagine this is your film, this is a cantilever and the surface is there. So on the back side of the tip, there is a laser light always falling on this one. So according to the morphology of this film, the film will vibrate, vibration will change according to the vibration. That small changes will monitor by the laser light reflections, because if you have the skin, if there is a change in morphology, the backlight reflection, the pathway will change. So those pathway is detected by the detector, then they will calculate the map, what will be the change in the morphology. This is basically, this technique is adopted in AFM, okay? But these changes, remember, these are nano level changes. That's why the tip itself, it's the whole thing is micrometer. The tip itself will be nano level change. So if the sample is too rough, we can't do that, because it will damage the tip. You see how is the tip size? Okay, even small tip. If it is a nanoscale material is there, then you can keep on use the surface and scan the film. Okay, so here we have a different type of method is forming. One is the tip actually touching this surface and scan. That is called contact mode things. Another mode is called tapping mode. You may have heard about tapping mode is the tip doesn't touch the surface. Instead of touching, it just vibrate on just a little bit distance away from this surface. Then because of this, the van der Waals force interaction, according to the morphology, the height changes and the reflection also, the vibration of this cantilever also change. These changes will be detected by laser signal. Then it will be translate to what is a map into what is the actual morphology of the signal. So there are two methods making contact mode and tapping mode, and they find out finally they find out what is this type of fiber morphology or nanoscale morphology, all the things. I'm just saying about even though we use a technique and do the morphology, how is it work? That also, if you know that how is it work, then you know how to prepare the sample, and we cannot use the very rough sample for this, otherwise you will spoil the tip. If you spoil, we don't know. Even when you scan the instrument, you have the question that you can't really see the tip, whether the tip is working or not. That we don't know. That one, we need to have some idea about if you don't have that, if the tip is already broken or if it is not there, you don't see the feature size. You don't see the right features, nanoscale feature. It always like a very plain surface. Okay, it will be misleading. So it will have some type of working knowledge on how the instrument works. Then only we can get enough required information from the data. Because just putting that, not like that. If you, for example, if you are putting any microscope, you just put the slide and see through, you can find out that's easy. Not like AFM is same as like that. Okay, because this is a somewhat different way of getting information. We are probing, from this one we find the information. So you should know that how is it working. Okay, so another thing is the information. You see, this is one of the examples how they do the morphology of the film. Okay, this is one of the thiophene based molecule. They have with the different molecular weight. As I said last class, molecular weight also affecting the device performance. Not only device performance. You see, when in the same molecule we have a different molecular weight, it's giving different morphology. At lower molecular weight 1.9 give a very fiber-like morphology, and at little bit higher again elongated type. But if we go and increase the morphology, the fiber is already gone. Some of the feature is coming. So this is one of the things. The molecular weight is affecting different things. Molecular weight, the morphology will reflect in the device performance. Okay. So those things we can get it from this AFM picture. This just the size is around 150 nanometer. You can see that at lower morphology, at low molecular weight, we are getting the very ribbon type of things like arrangement, very nice arrangements. But when you have the high molecule, almost we lose this type of regular arrangement. We are getting a zigzag arrangement of this fiber things. So all this information we can get it. This is from surface, whereas in GVAX we are getting the bulk information. Okay. Okay. So this is another work we have done with comparing both TM and SM, because like I said, TM is another tool to find out this morphology of things. So this is a TM picture. What we did, this one of these device fabrications, because again, as I said, morphology tuning is a very important factor to have the optimum device performance. Suppose in this case, we found that when you make this molecule, DTS, BTD, we have done some 12 years before. When you mix this one, we always get low performance. We are expecting this should be the high performance, we are only just getting. So what we done is, when we analyzed this morphology, it was bigger domain. It's more than 200 nanometer, which is not good for solar cell. What we have done is, in this mixer, we add little bit additives. There are small additives we add. That will drastically change the morphology. The bigger domain is broken and make a very small nanoscale morphology. Those things we can see that in AFM picture also. You see, the bigger morphology is got to very, very small type of morphology things. So when we have this one, you see how the device performance improved. It go from 2% to almost 6.4%. It's a huge difference. So this difference is only because of this morphology. Same material, same composition, same device structure, everything else. Just a simple morphology is changing the performance lot. If you don't capture this type of device fabrication technique, you will miss the opportunity for making good devices. So you have to have a little understanding. It's not like I can say one factor. Yesterday I talked about molecular design. Molecular design only is not a only factor. You need to make some people make a good device and good understanding of what is going on in the film, because It's not everything seen by your naked eye, because this nanoscale, you need to have tools see that. That tool you have to write, you have to use in the right way. And you have to understand what tool you are using, how the tools are functioning, then you have to adapt it, get the right information, then you have to correlate. Then only all those things work together, then only you can make a good physicist like this, good device physicist, okay? Because I see most of the people from physics side, engineering side, so you should know this one, even if you don't know the chemistry knowledge. So this one gives the good information about this one. Anyway, this type of device fabrication process technique I will discuss in detail in Thursday. Okay. So this one more technique is Kelvin probe. Okay, AFM not only one purpose to morphology, because AFM is, I said, the tip, right? The tip we can use normal tip, silicon tip. At the same time we can make a conductive tip like platinum iridium tip. Then the tip is made conductive. Then if you see the conductive tip on scanning on the surface of the electrode, then you can find out what is the potential difference. When you are conducting, it will conduct the charge. Those information from the same as AFM, just to change the tip, conducting tip like this. That's called Kelvin probe. So here what we do is instead of scanning, we use a conductive platinum iridium tip and scan it. So normally this will have some type of charge. Those potential difference will be captured by this tip. So it will give the contact potential. The contact potential thing, but is the voltage at tip and the voltage at the sample, the difference. Finally, you know that what is the surface potential of whatever the film you got. So those things you can find out from Kelvin probe microscopy. Okay. So and another AFM is called photoconductive AFM. Photoconductive AFM is, suppose you say the photoactive material, when you shine the light, it will generate the electron, right? So how to know that nanoscale level? I'm not saying bulk scale. In nanoscale level, which domain is actually giving electron? If you have a different domain, which domain? Sometimes some domain is not working. Which domain is it black domain is not generating anything? Which domain? Those things we can find out from photoconductive. Here in this instrument, what we are doing is the same as conducting tip AFM, but underneath we have the transparent surface. We have the laser light coming out. So the laser light illuminates the film with the light. On the top we are scanning, and whatever the current difference will be detected by this probe, and we can have the scanning. You can see the scanning. The conductive tips are having, because this map is according to the surface with respect to how much current, how much electron is detecting. Wherever is white spot, there is conducting there. Remaining spot is nothing, and there is no current out. Okay. Sometimes there is a donor acceptor, the donor acceptor domain, only the donor part will generate current, acceptor part will accept the current. So those things we can map here, which is the one. So this is a focused image where we can see the conductivity of the domain in this one. So the photoconductive AFM is another tool. We can say that nanoscale mapping of this photoactive layer, where is exactly the light harvesting happening, and that one we can probe using conducting probe, photoconducting AFM. Okay. So with this one, I will conclude this lecture. I hope I have explained to you some of the characterization, both photophysics as well as structural characterizations, which is important because not only this one, still a lot of techniques available. Those things are, even GVAX, we can say R-shocks. There is a lot of other techniques also is available. But due to time limit, I am only presenting the very important things factor. And hope this will helpful to at least you get to know this term, and go ahead and explore this one if any questions you ask me. Okay. The next lecture we do the OFET. Now next lecture we do photophysics. This one we doing tomorrow. I change. We do the photophysics of this one. Photophysics of organic semiconductor. Okay. How the excitonic. This one OFET we are doing tomorrow morning. Okay. If any questions you can. Which one? Yeah. Yeah, how you fabricating, how much sample, that's a different. Normally this device are in ITO, not silicon wafer. Yeah. Substrate effect also will make difference. What's arrangement? Finally, we make whatever the way you make it. How is it to arrange? That's the one. It can edge on, it can flash on, even isotropic, whatever things. We need to, so if it is not favorable arrangement, then we need to change the underneath layer, the bottom layer, we need to change. Sorry, which one? Yeah, if you want to, we need to do the different, that's why the device optimization. If the arrangement is not good, you don't see the right performance, then you explore, okay, arrangement is not good, then a lot of other technique we can change this arrangement, if you really want. No, not surface morphology. I'm saying different. Only the AFM is surface morphology. GVAX is a bulk. We can go into the probe. Yeah, roughness. Yeah. Right. Yeah. I didn't discuss here, but AFM only surface. AFM will tell a lot of things. Say roughness also we can get, because once you get a roughness, you will get a phase image, you will get an amplitude image, you will get a roughness, and you see even depth analysis, all the things. But I'm saying the very important things only in this one. If we talk about the topic, the AFM itself take 1 hour. That much information is there. I'm saying that what information only used for in this context only I'm talking. I'm not taking full depth of AFM. Yeah. Inclined angle and what it's getting, but the technology read is different. There is a reels you are talking about. No, now we are now this is, there are different Compton spectrum, photoelectric. We are using the reflection coating only. We need reflection. It's not absorb anything. Yeah. Okay. Yes. Yes. Spin coating. I just say spin coating. Spin coating itself, there is a lot of parameters there. Not only spin coating speed, make a thin film. Sometimes higher speed make a very good film. If you want higher film, then different, what is the concentration of psilocybin you have adjusted. Sometimes when you prepare concentration, the molecular weight will change the viscosity, because all molecular weight, if same weight, not only weight, different we need to have some viscous to make a film, right? So those things, when you have the new molecule first time, this is the initial stage of optimization at molecular weight. Not every material go the same type of material we can do. So I'm saying the only one, but every term is have a lot of work actually. Because it's okay now. 11:05 we go for a break. I think we will come back next lecture. I think Dr. Anandan will take care of. We are going to see one more photophysics in afternoon. Okay. Then afternoon we are also doing the hands-on experience of how to get it. I don't know how many of you use the absorption spectroscopy, band gap determination. You already use, you know that thing. Okay. So I said only the theory, but how to get actual data, how to fit it. Okay, this will be useful. We'll do it in afternoon. Okay, thank you.